data structure, where we have nodes, and these nodes are connected with the help of edges. We also have a root node, which is the starting point of the tree, and this is the node where we always start reading the data in the tree. Graph data structure is similar to the tree data structure, in the sense that we still have the nodes, which are also called the vertices of the graph. The singular form of this is called vertex, and these vertices are connected with the help of edges. So if you look at this graph, we have 7 nodes or 7 vertices in this graph. Now if we label these vertices alphabetically and we represent the vertices with V and the edges with E, the vertices of this graph would be A, B, C, D, E, F and G. And for the edges, from vertex A we have AB, AD and AE. From B we have BA, BD and BC. And similarly we have all these different edges from other vertices. Alright, so the graph can either be directed or an undirected graph. The graph that we previously looked at was an undirected graph. In undirected graph we have no direction tied to the edges. So if you look at this graph, we don't have any direction on any of the edges. We can travel from any node to the adjacent node and back. So if you see here, we can travel from node A to node B, and from node B we can travel back to node A. We can travel from node A to node D and back from D to A, from A to E and then back to A. In the similar way we can travel from any node to any adjacent node and back. Now if you look at the edges for this undirected graph, it would be this list. So we can travel from A to B, D and E, from B to A, D and C, from C to B, D and G, and so on. Alright, so next we have the directed graph. In directed graph we have direction tied to each of the edges. So if you look at this graph, we have arrows showing the edge directions. So for example, we can move from node A to node B, but we can't travel from node B back to node A. Let's look at the edges for this graph. So from A we'll have AB, from B we can travel to C, so we have BC, then we have C. We can't travel from C to any other node, so we don't have any edge here. Next we have D. From D we'll have the edges DC, DE and DF. From E we have EA, and finally we have F, from which we can't travel anywhere, so we don't have any edge. Alright, let's look at some graph terminology. So first of all we have path. A path to a node or vertex is a set of edges from starting vertex to the ending vertex. Let's say that we have this graph and we need a path from vertex E to vertex C. So we have vertex E, then we'll travel to vertex A, then B and then C. So the path in this case will be E, A, B and C. Next, a path can either be closed or a simple path. A closed path is a path where the starting and the ending nodes are same. So in this case, example of a closed path will be A, B, C and A, because starting and ending nodes are same, the A node. So we start from A, then B, then C, and finally we are back to the node A. So next we have simple path. A simple path is any path where the nodes are not repeated. Let's take this graph as an example. Now in this case, if we take the path C, A, B, C, D, this path is not going to be a simple path because the node C in this path is repeated. But if we take another path C, A, B, this is a simple path because no node in this path is repeated. Alright, so next we have loop. A loop is an edge that connects a node to itself. So if you look at this example, the node B is connected to itself by this edge. So this edge will be called a loop. Next we have the degree of a node. The number of nodes connecting a node to the graph is called the degree of that node. Let's look at this undirected graph first. If you look at the node A of this graph, there are 2 edges connected to this node. So the degree of node A would be 2. B has also 2 edges. So again, the degree of B will also be 2. C also has 2 edges. So the degree of C will be 2. Now, what happens if we have a loop within a node? So let's say that we have a loop on the node B here. When counting the number of edges, a loop is counted as 2. So for example, in this case, we have 2 normal edges. so we'll take 2 for these, and then we have a loop, so we'll add another 2. So 2 plus 2 is equal to 4, so the degree of node B here would be 4. Next we have a directed graph. In directed graph we have two types of degrees for each node, the in degree and the out degree. In degree means that the number of edges coming into the node, and the out degree means the number of edges going out of the node. If you look at this example, we don't have any edges coming into the node A, so the in degree of the A would be 0. But there are two edges going out of the node A, so the out degree of the A would be 2. Next we have the node B. There is one edge coming into the node, so the in degree would be 1, and there is one edge going out, so the out degree would also be 1. For C we have two edges coming in, so the in degree would be 2, but there are no edges going out, so the out degree would be 0. Now what happens when we have a loop in a directed graph? So let's say that we have a loop on the node B. Now there are two edges coming into the node, one normal edge and the other is the loop. So the in degree of this node would be 2. And similarly we have two edges going out of the node, a normal one and the other one for the loop, so the out degree will also be 2. Alright, so next we have a cycle graph. A cycle graph is a simple graph where we have all the nodes connected to each other, and the number of edges is equal to the number of nodes of the graph. So for example, if you look at these two graphs, both of these are cycle graphs because all the nodes are connected to each other and the number of nodes is equal to the number of edges. Next we have a connected graph. A connected graph is a graph where we can visit any node from any other node. The number of edges between the two nodes doesn't really matter. What's important is to have a path between two nodes. So for example, here is an undirected graph which is a connected graph because we can visit any node of the graph from any other node in the graph. But if we remove the edge between the node A and node D, the graph will no longer be a connected graph because we cannot visit all the nodes of the graph from any other node in the graph. This type of graph is called a disconnected graph. Alright, so next we have a complete graph. A complete graph is a graph where each node of the graph is connected to every other node of the graph with exactly one edge. So here is the example of two complete graphs because all the nodes of each of the graphs are connected to every other node of the graph. Alright, so next we have a weighted graph. A weighted graph is a graph where we have a value or weight assigned to an edge connecting two different nodes. So if you look at these two graphs, you can see that we have a weight written on top of each of the edge. So both of these graphs are weighted graphs. Next we have a simple graph. A simple graph is a graph which doesn't have any loops or the parallel edges. So if you look at these two graphs, both of them are not simple graphs because one has a loop and the other has a parallel edge. If we remove the loop from the first one and the parallel edge from the second one, both of these graphs will become simple graphs. Alright, so now that we know what the graph is, the different types of graphs and the terminologies, let's see how we can represent a graph programmatically. There are two ways to represent a graph, either by using the adjacency matrix or adjacency list. So first of all we have the adjacency matrix, in which we represent the graph using a two-dimensional array or a hash map. Let's say that we have this graph and we need to represent this using the adjacency matrix. So we will create a two-dimensional array where each dimension of the array has all the nodes of the graph. And then for each value slot, we'll either store 1, which means yes, we do have an edge from this node to the other node, or we will store 0, which means we don't have any edge. Let's look at the node 1. So the first value of the matrix is matrix of 1 of 1. Since we don't have any edge or a loop connecting the node 1 to the node 1, so we will put 0 here. Next we have 1 of 2. Now we do have an edge from node 1 to node 2, so we will put 1 here. Then we have 1 of 3. Again, we do have an edge from 1 to 3, so we will put 1 here. Now 1 of 4. Now we don't have any edge between 1 and 4, so we will put 0 here. And then we have 1 of 5. Again, no edge between 1 and 5, so we will put 0 here. Alright, so now we will move to the second row, which is the node 2. Now we do have an edge between 2 and 1, so we will put 1 here. 2 of 2 will be 0 because we don't have any edge between 2 and 2. 2 of 3 will be 1 because we do have an edge. 2 of 4 will be 1 because we do have an edge between 2 and 4. And 2 of 5 will be 0 again because we don't have any edge between 2 and 5. Similarly, we will fill up the values for node 3. So 3 has edges connecting it to 1, 2, 4 and 5. So these values will be 1 and the others will be 0. And in the same way, we will fill up the values for the node 4 and the 5 also. And this is how the adjacency matrix works. We have both dimensions of the array representing all the nodes of the graph, and we either put 0 to represent no edge between the nodes, or we put 1 to represent the presence of an edge between the nodes. For a weighted graph, we still have the same matrix, but in that case, instead of 1, we fill up the matrix with either the weight of the edge, or we put infinity if there is no edge between the nodes. So we don't put 1 and 0. For 1, we put the weight of the edge, and for 0, we put the infinity, which means that there is no edge between the two nodes. Alright, so next we have the adjacency list, where we use an array of linked lists to represent the graph. So if we look at the same graph here, we'll have a one-dimensional array of nodes, where each value of the array will hold the pointer to a linked list, which will be a list of all the nodes to which the current node has an edge with. Let's fill up this array to understand what we mean. So first of all, we have the node 1 here. Now 1 has edges to the node 2 and 3. So we'll create a linked list with the nodes 2 and 3, and we'll put the address of the list in the index 1 of this array. Next we have the node 2, which points to 1, 3 and 4. So we'll create a linked list with 1, 3 and 4, and we will put the address to that in the index 2. Next we have 3, which points to nodes 1, 2, 4 and 5. So we will create a linked list with 1, 2, 4 and 5 and put the address of that in the index 3. So next we have 4, which points to 2, 3 and 5. So again we'll create a linked list with 2, 3 and 5 and we will put that into the index 4. And finally we have the node 5, which points to 3 and 4. So we'll put the linked list with 3 and 4 into this node. And that is how you represent a graph using adjacency list. I've given the pros and cons of representing a graph with adjacency matrix and list in the description below, so make sure to check that out as well. Alright, so we finally have the use cases of the graph data structure. So they're used in the GPS systems, for example in Google Maps to identify the shortest path between two locations. In social networks, for example Facebook and Twitter have the social graph representing you and all your friends as nodes. Also they're used in the search engines, for example they're used to rank the pages and the search results as well, and so on. And that is all for the graph data structure. In the future videos we'll be covering different